He's the top expert on ICP emission spectroscopy, period. And that's not exaggeration.
Thanks.
So he's been working for Spectro. Now he's with Pure Lithium. He's vice president of technology, right?
Analytical services.
Right. So there is no sample in the world
That's true.
that Dion has not worked with or know how to deal with. And one more thing, so I had privilege to work for Dion for 8 years. That's why I have so much great handling. Please.
Does this auto?
Yes, it does.
Okay. And is there a laser or no? Oh, there is. Yeah, there is.
Oh, you
yeah,
got, okay.
Yeah, I got it. Okay. So we're going to talk specific. Does anyone do any lithium work here? No? Good. Oh, you have to leave. So my company, Pure Lithium, is a MIT startup with Dr. Dion Tsourides, who is a bit of a celebrity. If you don't know him, he's a material scientist from MIT, who, if you Google his name, you'll see him on the Stephen Colbert Show, like I said, and you'll see him in the MIT Gundam videos. I'm not loud enough? Oh my God. Well, all right, no problem. Good. Let's try that again. So, now I can't go far. And he developed this technology for a lithium metal battery, not lithium ion. And lithium metal batteries are really the holy grail, you know, of a future power supply. They're incredibly inexpensive to make, and most importantly, they require no graphite. No substrates like that. It's phenomenally easy to make the battery, so much so that it's a greener technology. We can actually create batteries from oil field brines. So we can reclaim, you know, this oil field water that's coming up, sitting there, and then being pumped back into the ground. We can monetize it for the oil companies and, you know, for battery companies, so that they're actually, you know, being greener, not requiring the mining of the lithium. So we're going to talk about specifically in this matrix. It's an easy sample to handle, and it is an impossible sample to handle because it's such a new industry. There are no true norms, ASTM, ISO, whatever. I am part of the ISO TC 133 committee, so we are working on that. But let's talk about the analytics first. You really have 3 ways to look at the sample. You know, you've got AA, mass spec, and ICP-OES. You can use AA. It's an antiquated technique. It is inexpensive, but it's, okay, this is, hold on. Let's try that again. Okay, it is inexpensive, but there are some issues, you know, with safety, and it's not truly, for our needs, going to provide the performance we need. We need the halogens as well. One of the reasons for that is chlorine. We don't want lithium chloride as any of the lithium form of the raw material we're working with. ICP-MS spec gives you high sensitivity. It does not, regardless of all the papers and everything, it does not tolerate total dissolved solids for a true production environment. You have a lot of maintenance, and the other problem is if you do a large serial dilution, and that's one of the biggest problems with this. You know, people will look at a battery sample and be like, oh my gosh, look, that sample's the size of a quarter, and this is going to be great. It's going to be a very small dilution, and then they weigh it out and they realize it's 3 milligrams. You know, and next thing you know, you're doing a 30,000-fold dilution. And you happen to make a mistake because you went to McDonald's that day, had a little sodium on your hands, you contaminated it with 50 ppbs, you're multiplying it by 30,000, and now all of a sudden your Pure Lithium has sodium in it. So ICP-OES is what we homed in on, and almost everyone in the industry uses. I'd say it is the preferential technique for this. You can cram up to 30% total dissolved solids. You can run organics. So when you're talking about an electrolyte, you can run EC, you can run DMC, so dimethyl carbonate, all these electrolyte materials, you can pump directly into the ICP. You can calibrate it using isopropyl alcohol and aqueous standards, and you get a pretty good matrix match. You can run the alloys, so if you're doing, a copper substrate or an aluminum substrate on the cathode, you can digest that, run it into the ICP. It gives you the flexibility to pretty much cover anything that comes through the door, including, if you want to do lithium-ion batteries and do graphite, you can even take the graphite and run it as a slurry. You can grind it, and you can take the graphite. You can buy commercially available graphite. I've published papers in ceramic industry on this. As long as you have the right nebulizer, we'll get to that in a bit, and your ICP can tolerate the particle size, because some plasmas cannot. They're all not created equal. You have the ability to run things as a slurry. Okay, this is a plasma with an oil field brine on it. Let me start the video very quickly just so you can see it. So that's, 30% sodium matrix or oil field brine. There's a ton of sulfur in that too. So these samples have organic residue in them too. So that's another thing you have to watch out for when you're running this. But let's talk about the observation and really dissect the plasma. There's two types of views, if those of you who run ICP. There's radial, there's axial. Dual view is not a view, it's a switching between the two. So you're either looking at something axially or you're looking at something radially. Unfortunately, if you try to look at both at the same time, you start to reduce your performance range, and you give up elements like, aluminum 167 and phosphorus at 177. So you really, are going to look at the plasma radially, and when you do so, you're looking through this zone right here. It is the cleanest emission zone. If you ever run yttrium through your plasma, you will see orange here, blue here, and red up here. Red, very bad. Red is dead. You know that expression? Red is dead. You want to stay away from that recombination zone. This excitation zone here causes you problems. Minimal, you can usually deal with them, but unfortunately, where they cause the biggest problems is group 1 elements. And last time I checked, lithium was a group 1 element. So we'll talk about that later on. So really, this is going to give you your best stability, highest matrix tolerance, your higher dynamic range, less matrix effects, but you're going to trade off sensitivity. And normally that doesn't matter unless you start doing large dilutions or you're looking for something at extremely low levels. Axial plasma, same thing, except now because we're looking down a longer path length, we get better sensitivity. However, you have EIE effects to work with, slightly less tolerance to total dissolved solids. You can go up to 20% versus 30% routinely. Not the greatest for organics because you get a high carbon background. Again, you can bleed in a little oxygen and resolve this. So this, this is great if you're pushing sensitivity or you're very, very comfortable running an axial plasma because it is going to require more work. Regardless, everything we're talking about here, you can do radially or axially. It just requires a little bit more preparation and skill to run axially. All right. So this is a very interesting slide. This is 50 ppms of sodium and 200 ppbs of potassium. The green is 200 ppbs of potassium in water. The red is 200 ppbs of potassium with 50 ppm of sodium. Sodium in it. That's your EIE effect, easily ionizable effect. So when everything stays the same, you have very good accuracy. When the group 1 and group 2 elements start changing, percent levels in one sample, trace levels in another, you can have anywhere from 50 to 200% error on your group 1 elements. Sodium, potassium, and lithium are the three big ones. It affects calcium, magnesium, barium, strontium, but not nearly as much. We're really talking about the group 1 elements here. And I cannot tell you how many certified lithium, metal standards I've gotten or raw material I've gotten in that is 99.9999% pure. Not happening. what they do is very clever. They selectively pick 5 or 6 elements to analyze, and then they tell you how pure it is. And then when you go and you run it in ICP and you start seeing peaks everywhere, you're like, this is not 99.99 whatever % pure. So let's look at axial and radial. So again, the effect is much worse on axial. It's not nearly as relevant on radial. However, remember, we're talking ppbs here. When you start talking % levels, what you see here still happens here. Don't let anyone tell you that's not the case. It absolutely happens. It just shifts higher in the concentration range. So you are going to deal with this effect regardless, unless you have a matrix that stays very, very constant. And mine does not. It's a research environment, so I have no idea what's coming through that door at any point in time. So please keep that in mind, that even though this is a much easier way to handle, you're going to get better linearity and there's going to be less issue. If you pump enough sodium in there, if you start talking sodium at % levels, and then you're looking at trace lithium or potassium, you're going to see the same effect on a radial system. This is the calibration effect. So on the right is the potassium in that sodium matrix, not affected. On the left, this is a radial, this is axial. So you can see there's a much more linear curve. What happens, as I mentioned before, when you get above 50 ppm, when you start talking about, you know, hundreds or thousands, this is going to kick out. It's going to look just like this. It's going to look like this. The only difference is that's not going to be 50, it's going to be 500 and then 5,000. Okay? So it is something you have to deal with. Oh. I feel like a dog tethered to a...
Handle spectrometers.
I cannot handle this. He's chained me. This is his dream. So, all right. So, let's talk about all of this in review. When you're running these samples and you're looking for accuracy and precision with regards to the group 1, group 2 elements, and obviously everything else, but everything else is much, much easier to handle by ICP-OES. It's a slightly quadratic curve, and an internal standard will fix it. You need to deal with the EIE effect, especially if your total dissolved solids are changing, okay? So for us in the brine matrix, you know, when we get a brine out of Midland, Texas, or a brine out of the Middle East, they're very, very different, okay? So you want to be careful when you calibrate. Okay, I cannot stress this enough. If you think you're going to take your brine sample, or you're going to take your metallurgical sample and you're going to send it out to Joe's environmental lab. By the way, if anyone has an environmental lab, I don't mean to insult you now, but they're going to run it by an EPA protocol. They are not going to run it by a proper calibration curve. So, you know, with alloys, you want to follow an ASTM procedure. You know, with, let's say a brine, you want to run matrix match. Oh, that was interesting. I see the light. So the bottom line is, if you want to get the most accurate, precise results, there's no substitute for a method of standard addition. It's a lot of work. A lot of people don't want to do it, but if you have enough material, you split it into 4 or 5 aliquots and you start spiking it, you know, it will back calculate the concentration in it, it will eliminate your matrix effects, and it will give you absolutely the best precision and accuracy. Unfortunately, some of us have to follow regulatory, you know, QC procedures, and some methodology does not consider standard addition the right way to do things. So a matrix match as best you can. There's ways around it. When we run dimethyl carbonate, we use isopropyl alcohol, straight isopropyl alcohol, or 90% I should say, isopropyl alcohol, and we adjust it so that the carbon bands are similar, and then we add an internal standard and we get the transport effects that way. Dilution factor. The less you can dilute, the better. I mean, I can, especially when you're working with something like lithium, I cannot tell you, you know, how important it is to have a good balance. When I walked into this lab originally, they were using regular, you know, 4 decimal place balances. You need at minimum a semi-micro balance or a micro balance. And for those of you who don't know, you're talking about 10-fold more expensive balance to go to a micro balance. Semi is good enough. but you need at least a semi, because like I said, when you're on there and you're measuring, sometimes you're not looking at 0.1 or 0.01 grams. You're looking at 0.0003 grams, and you're diluting up to 10 mils, and all of a sudden you have a 1,000 to 3,000 fold dilution, and any mistakes you make there are going to be multiplied by that error. Accuracy bias, again, can be 100% depending on sample prep. That's your mechanical error. If your pipette's not good, if your balance is not good. A plasma view, if you're running axially and you're not compensating for the EIE effects. And of course, your calibration strategy. Are you running water and then you're trying, aqueous standards, and you're trying to run an oil afterwards? Not such a good idea. So keep that in mind. ICP-OES and we have done a round robin. We've sent them all out by XRF, ICP, ICP-MS spec. You just get the most consistent numbers off an ICP-OES for my industry, for what we're doing. A radial view is definitely going to make your life much, much easier. So if you have the sensitivity and you don't need to push the sensitivity, I cannot stress enough, you will be a much happier place if you stick with radial and avoid axial. However, axial will work. Just make sure you're using the right internal standards. In our case, it has to be cesium and yttrium. We need both, depending on the analyte. And try to match atomic lines with atomic lines and ionic lines with ionic lines. That's the last thing I talk about. Like I said before, it's nice to have a dual view system, but if you're running dual view, you're just wasting time for these particular samples. You're better off dealing with it initially, saying, I can get the most performance out of this radially or the most performance out of this axially, and I'm going to suit my calibration for that. Okay? If you do this, you'll get good, accurate results. If not, I'm not kidding you. You will be 50 to 200% off on your Group 1 elements. All right, what do we run? We run typically, as I said before, oil field brines, usually 1 to 2%, but we can go up to 30%. We run high purity lithium metal. We run all the reagents that come in, the so-called high purity acids and DI waters and everything. A lot of organic electrolytes, which is what we use in the battery manufacturing. The substrates for the cathode, so they can be copper, aluminum, iron. And we even run our polymers. So we have a very, very unique selective polymer membrane. So just very quickly to tell you what we do. So you say, how do you make a battery out of an oil field brine? Well, you put this polymer membrane in the middle. On one side, you fill it with the electrolyte and a certain amount of lithium already in there, and you put the cathode in there. On the other side, you put your salt water, okay, your oil field brine. And the cathode will be deposited electrochemically to create the battery. So the membrane only lets the lithium through. It blocks everything else, okay? This is really the core to our technology. So as we deplete the lithium on this side, it starts to draw lithium from the salt water. And that's how this battery technology works. And people will say, well, how do I know? Because you put lithium on one side, how do I know it's actually pulling lithium on the other side? And that was very good. So what we did was we developed an experiment where we would have lithium-7 in the electrolyte and lithium-6 in the brine. We'd make a synthetic brine. And what's unique about this is the ICP we have, and this is not common at all for ICPs, but the ICP we use can actually separate lithium-6 and lithium-7. So we did a calibration curve of lithium-6 and lithium-7, and you could actually see, as we applied current, the lithium-6 depositing after we redigested the cathode. One thing you need to consider is, what's 5 minutes? Perfect. I'm almost done. Don't bother me, okay? Is your introduction system. As the previous speaker had mentioned, there's an Achilles heel to all ICPs. If you cannot get the sample from A to B consistently, you're going to have a problem. My matrices change. Like I said, we'll run slurries, we'll run, alloys, we'll run everything. I need a nebulizer that's bulletproof, otherwise I'm going to be babysitting the technician in the lab who's babysitting the ICP. So, you know, your nebulizer, your torch configuration, they're very, very important, okay? Think about this stuff. Do I want borosilicate glass? Well, not if you're looking for low boron, okay? Do I want quartz? Do I want synthetic? You know, well, synthetics are great, but they don't wet well, so that's going to affect your precision. There's a lot of questions you need to ask. But ultimately, it starts with your nebulizer. And, you know, assuming you don't have a bad peristaltic pump, short-term and long-term precision really come down to how well your aerosol is created, mixed, and delivered to the plasma, and what consistency it has. And the construction material. As I said before, if you want to do boron and silicon, it's critical. So the ICP we use is a Spectro Arcos, and it uses a roll-in circle, and that's the main reason that the resolution at 670 for the lithium is so high. It separates it, so lithium 6 will actually fall slightly off from lithium 7, and if you run the two next to each other, you will physically see two peaks. The setup on our particular system is very similar to the previous picture you saw. I do run axially, even though I told you it's not the greatest way to do it. I just don't have time to go back and check for traces. So I do run axially. I use cesium and yttrium. I just tee it in. I use just a simple T connector, so I don't have to worry about the internal standard. Unless it runs out, then I have problems. But other than that, I just put about a liter of the internal standard behind the auto sampler and let it go. This is the Ultem. It is the ultimate. It's made out of Ultem, and it's worked out great for us. Very, very low maintenance. We've dropped it on occasions. Sorry, Sergey. Just don't drop it on the tip. But it is a very, very simple nebulizer to use, and we've had very, very good success with it, with virtually all our matrices except maybe the most aggressive organic solvents, okay? So quick look at some precision data. The relative standard deviation here is we're typically under 1%. We're typically around, you know, anywhere from, I'd say 0.5 to 0.7 typically. Here you'll see both certified reference materials, which is the QC1, and real oil field brines below. So you can see there's only a small degradation when you go, if we look at the beryllium, from 0.1 to 0.7 on the following sample. On the chrome, which is one we look at closely, it stays consistent. So the bottom line is, it doesn't matter if you're running a synthetic clean matrix or a nasty matrix, it's good. This is lithium, which is obviously something that's very, very important to me. The 670 line is incredibly sensitive on this instrument. It's parts per trillion. And I'm not kidding you, it's parts per trillion. So we will also use 460, 323, and 274 lithium. But again, RSD's typically well under 1% in this brine matrix. So conclusions. Know what you're doing, but with regards to lithium, you have to understand, currently there's really no governing body that has an ASTM ISO method. I am on the ISO TC 333 committee. We are working on developing procedures for analyzing this material, but as you can imagine, it's a committee, so the whole world's involved in it, so it's going to be a little bit of a drawn-out process. When you send samples out, make sure that they understand what the matrix is. Please don't let an oil lab run your drinking waters, and don't let a drinking water lab run your metallurgical samples. You're going to regret it. Sending out samples is something you want to avoid if you can. You really just want to check if you think there's something wrong. Best way to do it is to do it inside. So bottom line is, you know, understand what your sample matrix is, what you're trying to accomplish with your calibration, and you know, watch your introduction system, know your spectrometer limitations, and make sure you do this as accurate a sample prep as you can. Questions? And I don't need this anymore.